promised. I apologize ahead of time. My voice is still getting conditioned to talking, and in my earlier class today, I already talked for an hour and 15 minutes, so it's just, you just bear with me. So I have water, and if I take a break, I apologize. I'll get better by the end, okay? So we're going to start with Chapter 2, Foundation. You should have all at least done some of the reading. And I know in the beginning it's a little tough because you don't exactly know the kinds of stuff I'm going to emphasize or whatever. So we learn together, right? You learn the kinds of things I think is important. At the same time, you'll kind of learn how to read the book appropriately and pick out the right sorts of things. The other thing is I hope you all brought your sketchbooks that I talked about. Nods. Yes? Did you bring them? Okay. So there will be a few drawings that we're going to take a break. You guys are going to draw it, and then we'll continue with me talking, okay, because I want you to have to draw it because it'll help ingrain these certain details in your head so you understand how things go together. Make sense? Good. Okay, so Chapter 2, Foundations, if we can go forward. First one's always tough. Okay, so a foundation is what's underfoot, okay, and it needs to be able to support what's called dead load. It needs to be able to support live load. It needs to be able to support rain and snow loads, wind loads, seismic loads, soil pressure, uplift, those sorts of things. So really, it deals with a lot of this loading conditions, and it's really important in a building. Okay? Let's talk about the individual loads specifically so that you understand each piece. Okay? So, a dead load is the combined weight of all the permanent, non-movable things in the building. Okay? So the key here is the permanent. It's the structural frames. It's the walls. Right? It's things that are permanently attached to the building. So something like this table wouldn't be dead load, okay, because it's movable. Something that's built in, say this table, we're assuming it's built in, okay, this would be considered dead load. So it's the things that are built in, the things that, like this chalkboard is dead load. It's attached to the wall. Does that make sense? Okay, so that's dead load. It's things that's always in the building because it's attached to the building itself. Okay, and of course, things that are the building, the floor, the walls, the roof, that kind of stuff is, of course, dead load as well. Okay? So live load is anything that can be moved around by the occupants. So these tables can be moved around. You can move your chairs around. We're in the building. We move around, right? That would be a live load. Does that make sense? Yeah? Nods? Good. Okay? So it's just things that can be moved. It doesn't have to be alive. So your animal or your pet certainly would be live load, but the table is equally live in this context. Okay? How about rain and snow load? Okay? Rain, not so much. It's not that big of a deal. Okay? If you have a flat roof, you have the ability to pond usually because roofs are never perfect. Okay? So that in that case, the rain load would matter. There's some weight to the water. Okay? If it's a pitched roof, not too big of a deal for rain because it's not going to be enough rain to actually cause too much loading. But certainly if you're up in the mountains and you get some snow, you'd have to deal with snow loading, right? So snow can be really heavy. It can sit for long periods of time and can significantly add to the weight of your building. Okay? What about wind load? Wind load should be self-explanatory, right? The thing about wind load is it's not the type of load that we've previously been talking about. Everything else, right, dead load, live load, that's all weight that's pressing down on the building foundation, pretty much directly. Okay? Sure, I guess somebody could come running across the room and stop and cause a little bit of sideways momentum, right? Not really that realistic, okay? But something like wind certainly could press straight down if the wind was coming down on your house, but it can also press from the side, okay? And if the wind is pressing from the side, it's going to want to blow the house off the foundation, okay? So you have to think of wind load as not being a vertical force, but a lateral force pushing to the side. Okay, so how the foundation handles that force is very different than how it handles the vertical load. Okay? So, seismic load. Okay? Seismic load is very similar to wind load, okay? But it's unpredictable as to when it's going to occur, obviously. Seismic translates to earthquake. Okay? So, there are forces of movement during an earthquake, and the problem with seismic loads is it's both horizontal and vertical loading. Okay, the worst types of earthquakes, right, occur and do like this, like a wave. Okay, so from that epicenter of the earthquake, it's going to cause a ripple effect through the ground and through the buildings. So you're going to have both uplift and lateral force acting on your building at the same time, right? So it's going to do this. Okay, anybody ever been in a skyscraper during an earthquake? No? Okay, it's a wild experience, okay, because the floors will actually do this. Right? Because they're designed to bend a little bit and flex. If they were perfectly rigid, right, you'd have the risk of something breaking. And so we'd rather have it flex a little bit. Okay? So same thing happens in a smaller building, okay? But in your house, you don't have steel, you're not going to flex like that. You're just going to feel the shake. Okay? And earthquakes, of course, differ in their intensity, their magnitude, right? And how big those waves are. So how many people were around during the 89 earthquake here? Okay, a few people. Do you remember what that felt like? Okay? I remember what it felt like. I remember feeling like I lifted up in the air and I went back down a few times. Okay? And so that kind of a movement, right, is that's a vertical load, but it also is a wave that occurs going in horizontal fashion. So if you've experienced it, sometimes it helps to think back on it. Okay, so that's seismic loading. Doesn't happen everywhere in the world. Happens a lot around here, right, and along the rest of the Pacific Rim. Less so on the East Coast. Okay, so defining a satisfactory foundation. You know, what's important to a foundation? One, it needs to be safe against structural failure. Okay, that's the first most important thing. Okay, if the foundation fails, the building collapses, we're in bad shape. Okay, so we've got to have a foundation that can support that. Okay, the next thing is that a foundation shouldn't settle in a way such that the building becomes unusable or parts of it don't settle correctly compared to other parts, so you end up with the cockeyed door frames and that sort of thing. So a foundation wants to keep the building relatively level, right, and allow it to still maintain its basic functions. Okay, because if it doesn't do that, then obviously the foundation has failed to the point where you can't use the building, which defeats the purpose of having the building in the first place. Okay? The other thing is that it needs to be technically and economically feasible to build it in the first place. Okay? And this is a challenging one because building a foundation can be a very expensive undertaking, and so how, sure, you could design a super strong foundation, but at the same time, if it costs too much for the scope of the building, you're not going to want to do it. So it needs to be economically feasible, and you need to be able to actually make the foundation. So certainly you could engineer something, right, that was really strong, but you have to be able to actually physically build it, which is a big challenge as well. Okay, so let's talk a little bit about settlement. Okay, and can anybody define settlement? A little bit? Evan, go ahead. Well, you're sitting right next to each other, so this is going to be impossible. One of you, speak.
It's when the foundation, when the compact earth starts settling and losing water weight, the building starts to sink a little bit.
Okay, anything to add? Feels good? Okay. Exactly. So when we're talking about settlement, the idea of settlement is that over time, right, the placement of your foundation in elevation is slowly going to sink. Okay, because the soil is going to compact, stuff is going to happen in the soils that are going to allow that to happen. Okay, so if your building is built on bedrock, okay, it's probably not going to settle much, which is a good thing. Okay, which is why people love building on bedrock. Okay, if you're on another type of soil, and we'll go through all the rest of the types of soil, okay, that amount of settlement is really going to vary. Okay, and that's something you have to be very careful of, which is why a lot of times if you're going to do a building, you need some kind of a soils report. Okay, before you can design the foundation, you need to know what type of soil you're dealing with. The different types of settlement can also vary. Okay, so we're going to talk a little bit about the different types of settlement. So the first one is called uniform settlement. And these are two images right out of the book. You probably saw it if you did the reading. Okay, so we build our building, and it sits on this ground plane. Okay? In uniform settlement, the ground settles, right, due to the weight of the building or other factors that are acting on it, and it settles uniformly. Okay, so the building is still level, right, but it's just depressed. And obviously this is exaggerated a little bit. Your building's not going to sink 4 feet. Okay, but we can understand the idea, right? Just the whole building sinks just a little bit. Okay. The other type is called differential settlement, and this is where it becomes really problematic. Okay, and this happens all the time, to bigger or lesser degrees. And we'll talk about examples in just a second. So here, okay, building before settlement, same condition that we just talked about. When we move to differential settlement, the ground varies in terms of how it settles. Okay, this is particularly abundant in clay soil. Okay, and we'll talk about that when we get to clay soil a little bit as to why it happens. Okay, so this particular piece of the building has settled more than this piece and that piece. Okay? So what happens is your building isn't exactly level anymore. Okay? And if it does it to this extent, your building's going to start to fail. Okay? So it just depends on how much settlement occurs as to is the building going to fail or not. Okay? There is always going to be some, and what we really shoot for is this. Okay? This is ideal. This is the ideal conditions. This is what we're looking for. Certainly if it's on bedrock, then we don't have to worry about it because it's not going to settle at all. Okay? So let's talk a little bit about the different types of soils. Okay? And so the first thing we're going to talk about is rock. And rock is just a continuous mass of solid material for the context of this class. Certainly there are different types. You know, we have our granites and we have our marbles and our limestones, and there's variations in the types and how strong they are and whatever. But for the scope of this class, rock is rock. Okay? And so, generally speaking, to confirm that you are actually dealing with rock, right, it can only be removed if you're going to blast it or drill it. Okay? If you can remove it with a backhoe, then it's a whole bunch of smaller rocks, which is not quite what we're talking about here. This is solid rock. Okay? So you need a blasting. You need one of those epoxies that actually drill. You fill it with epoxy. It cracks the rock. That sort of thing. Okay? That's how they make, you know, like you get granite sheets for your counter. I'm going off on some tangent, but sometimes I do this, right? You know that you got the granite sheets for your counter. So if you've ever gone around and looked at the fabricator shop, anybody ever do that? Shopping for granite with like their parents or themselves or something like that? A few people. Okay. If you go around, you notice the edges always have these little circles in them. Okay. If they're untreated edges. Okay. Those little circles are where they've drilled and then they've injected it with epoxy, which then splits the rock apart from the next sheet of rock. Okay. So that's how it works. Anyway, doesn't really matter. Okay. The thing about rock is it's never truly monolithic. So it's not this one giant slab of rock. If you've ever been hiking in the mountains, you know this anyway. Okay? There are always these little cracks that run through it. But for the scope of building on top of it, we're going to consider it solid. Because these cracks are really negligible in that sense. Okay? It's not going to settle. Unless the building slides off the hillside or something like that. But we're not going to go there. Okay? So, it is the most stable thing to build on. Okay? And it should make some intuitive sense. You have a big giant rock. You build your building on a big giant rock. It's a nice stable surface. It's not going to go anywhere. That's good. It's not going to settle. It is what it is. Okay. As we move on, the rocks can be broken down, okay, into boulder and cobble. A boulder, by definition, is too large to be lifted by one hand. You need at least two hands, or maybe a forklift, or maybe you can't move it at all. Okay. So something like this, okay, moved by glaciers, this would qualify as a boulder. Okay. Then we also have cobble. Okay, and cobble shouldn't be too hard to define because you've all heard of cobblestones before, right? The paving material that they used to use. A cobblestone can be lifted by one hand. Okay, certainly it might be awkward, but you can theoretically lift it by one hand. So that gives you some size parameter. Okay, and then we move down to gravel. Okay, this is the next type of soil that we're really going to be talking about. And it's a particle that can be easily lifted between the thumb and forefinger. Right? More than half the particles are larger than 0.19 inches in diameter and smaller than 3 inches in diameter. Okay, so we're talking, you know, rocks that are about like this up to rocks that are about like this. Okay? So that mixture of rocks is called gravel. And so this is another type of soil that we could be building on. Sometimes this has bigger chunks in it. Okay? But we're going to consider it as that kind of uniform piece. So that's gravel. How many people have been to the beach? I hope so, okay? If not, you're missing out, okay? The beach has plenty of what's called sand, okay? And you guys think of it in terms of that. Probably never really thought about building on it, right? But my guess is you have a pretty intuitive understanding of how sand works if you've ever been to the beach, right? And you've walked barefoot. So you understand it's a little squishy. Okay, and we're going to talk about that in just a second. So individual particles of sand can be seen, but can't be easily picked up between your fingers. Sure, okay, you could get the particles of sand and you could slowly try to get one piece, okay? But realistically, it's really hard to pick up one piece of sand, okay? They're usually between 0.19 and 0.003 inches in diameter, okay? The next type is called silt, okay? And silt has particles that are too small to be seen unaided, okay? And in this context, it's a pretty blown up shot. You can see the fingerprint here, so you have some idea of the size of this, right? And there are these little bitty tiny dots, okay? So these are really, really, really small pieces, okay? So we go from gravel, big pieces, right, to sand. You can see the individual pieces, but you can't pick them up, to silt, where you can't see these individual pieces. Okay, we're going to talk about each of the properties of these in relation to foundations in just a second. Then we end up with clay. Okay, my guess is a lot of your houses are built on clay because clay is a very common soil around here. Okay, so clay doesn't have round spherical particles like sand does, right? Like gravel does, roughly. Okay, it has these little flat plate. Think of a dinner plate, right? It's flat but kind of round. Okay, that's the particle of clay. Okay, it's really, really small. So 0.0002 inches in diameter. So really small. And when you add water, it expands and contracts a lot. And that's the key thing about it. Okay? So you guys have probably seen this kind of stuff before, right? If you ever see ground that cracks up like this, it's definitely clay. Okay, and then the final type of soil that we'll talk about is called organic soil. How many people garden? A little bit? Not too many people. Okay? If you garden, right, or if you go to Home Depot and buy, potting soil or garden soil or something like that, it is this. It's organic soil. And I don't mean organic in the sense of I'm going to buy organic fruit. I mean organic in the terms of it's made up of organic particles. Okay? So these particles are slowly decomposing. So generally speaking, this is a soft, spongy material, right, that's you can easily compress. If you ever stood on it, you can tell that it compresses really easily. And those decaying pieces are great for growing things, right? But they're not great for building a building on because they compress really easily. Okay, so let's talk about the properties that define how these various materials work in terms of building on them and why you might like one or dislike another. Okay? So shear resistance, okay, is the varying ability for one particle to slide past another particle. Okay, so let's say I have these pieces of gravel. They're kind of jagged, okay, and I were to try to rub them across one another, they tend to stick. They wouldn't like to run across one another. Okay, if I had a whole bunch of marbles, right, that were perfectly round, they wouldn't stick. They'd slide back and forth across one another. Okay, so the same concept occurs as we go through these various materials. So let's say sand, for example. Roughly round particles, they're going to slide past one another pretty easily. Okay, so they're going to have a high or a low shear resistance because they're going to slide past each other. Okay, gravel, jagged edges, high shear resistance. They're not going to slide past one another. Okay, so that's what it's saying here. The more angular facets the surface has, the more shear resistance it will have. Okay, so these two terms are really important to learn. It's going to be cohesive soil and cohesionless soil. Okay, and if you try to spell check cohesionless, it's not in any dictionary, but it's in your book. Okay, so cohesionless is a type of soil that has very low shear resistance, thereby allowing the particles to freely pass one another. Okay, what would be a good example of this material? Sand. Sand is the best example. Okay, so you've been out at the beach, right? You go to put your foot somewhere, and it slides a little bit, right? That sliding is this low shear resistance. Okay, if you ever try to build a sandcastle, right, without water, obviously, it's going to always taper out to the sides, right? It's not going to stay this nice towery shape. Okay, that's because it has this low shear resistance, which classifies it as cohesionless soil. Okay, cohesive sticks together, cohesionless dissipates. Okay? What if you put this material inside of a concrete box, or for that matter, put it inside of something that was clay soil around it? Does this property change?
Yeah.
What do you think? I'd say yes. Okay, so let's say you fill a concrete block or a bucket. Let's take a 5-gallon bucket, you fill it with sand. Okay? If you stand on it, will it support you? Yeah. Okay. So if this type of soil is surrounded by another type of soil or rock that is cohesive soil, right, something that sticks together, this soil can support quite a bit of weight. But if it's not surrounded by that, it's going to have a tendency to slide, right, which is going to cause all the issues like you guys have seen the Pacifica buildings that are hanging on the edge of the cliff that have been there for however many years, right? That every year they come up on the news, oh, the rain's coming and they're going to fall off the cliff. You guys know what I'm talking about?
Yeah.
Right? Okay? They're built on sand, right? There is no boundary holding that sand in, right? Sand is a cohesionless soil, so when it's exposed, it's going to slip away. Therefore, the building's going to fall over, right? So this is a fundamental problem with how you built the foundation in the first place. Okay? So that's cohesionless soil. So let's talk about cohesive soil, which is the exact opposite of cohesionless soil. Okay? And it's a material that has a high shear resistance, right? So it's not going to want to slide. Okay? And how about an example of that? Gravel. Okay? Bedrock is an unfair example, so we're not going to use that. Okay? But gravel is a great example. Jagged edges, right? The pieces locked together, right? They're not going to slough off easily, and they can support more weight because of it. Okay? Which is nice. You don't have to surround it with anything. Okay? So, thinking ahead, if you did any of the reading, how might the type of soil influence the excavation that you'd have to do if you were going to dig a hole?
Cohesive soil is a lot easier to dig out because it keeps the shape after you dig it out. Whereas with sand, for example, you start digging it starts caving in.
Bingo. Dead on. Okay? So this is going to change the way we have to excavate a particular site a great deal. Okay? So if, for example, you go out and you're in the beach, right, and you dig a hole, right, it's going to be really hard to dig a hole with perfectly straight sides. Right? This isn't going to work because the sides are always going to want to slough back in. Okay? But if you're in some kind of a very cohesive soil, gravel, clay, right, you can dig this almost straight down on the sides, right, and it's not going to collapse in on the side. So it depends on the effort required to dig, depending on the type of soil you have, right? So this would be sand. So you're going to have to do this type of an excavation to be able to get this whole same area clear at the bottom. So there's a lot more that needs to be excavated in this type of soil. And that's certainly something to consider when you're building. Okay, so these are a table, I think this is out of your book, yeah, it's figure 2.5. Allowable foundation pressures. Okay, I'm not going to ask you to memorize any of this stuff. This is the kind of thing that if you really need to know, you're going to look it up in a book. Right? You don't need to know these specifically, but it gives you some idea. Okay, so these are pounds per square foot of weight that this soil can support. 12,000 pounds per square foot is in bedrock, and we come all the way down to clay, and it's only 1,500 pounds per square foot. Okay, so that's a major difference when you're thinking about the weight of a building. So if, for example, you were in San Francisco and you wanted to build a skyscraper, what soil do you hope you have? Right? You totally hope you have bedrock. So there are a whole bunch of tricks when you design the foundation so that you can actually build heavy buildings in these other types of soil. But if you can find bedrock, that's always the best. And we're going to talk about ways that you might be able to get bedrock even though there's a lot of distance between where the surface is and where the bedrock is. Okay, so test your knowledge here. Take a moment. You probably want to write this down in your sketchbook. Rank the following, right, in terms of the soil that can bear the most weight to the soil that can bear the least weight. Okay, you guys ready? Answer? Okay, so here we go. Bearing the most weight, we start at bedrock. Okay, next most weight is gravel, followed by sand, followed by clay, and organic. This is a trick, because you should never build a building on organic soil. Okay, so if you were going to build a building, you would scrape away all that organic top layer of soil, what's called topsoil a lot of times, so that you could get to whatever the real soil is underneath. So if, for example, you were going to go build a garden shed in your backyard, right, you wouldn't just put your foundation on top of your lawn. That would be a bad idea. Okay? You would want to get rid of your lawn and the underlayment soil that's involved, get down to whatever the base material is in your backyard. Okay? Make sense to everybody? Okay, these kinds of questions love to show up later on. Right? Okay. So let's talk about another thing that can happen with soil. And this is kind of scary if you think about it. Anybody heard of this before? Okay, if you buy a house where happens, you have to sign a waiver saying, I know this happens. Okay? This is called liquefaction. Okay? And so if you're in an area, Bay Area, right, with a very high earthquake risk, Bay Area, right, there are certain types of soil, right, sands and silts, with a really high water table and a lot of water in them. And in that particular area, during an earthquake, that soil can shift from being a solid to being a liquid. That's kind of problematic, right? So the best example of this, it's temporary. Okay, it'll shift back. Best example of this, Alameda. Anybody live in Alameda? Oh, good. So I can blast Alameda and nobody's going to be like, oh my God, I don't want to go home. Okay, good. Okay, so Alameda was built, okay, with fill. Okay, so they needed the Naval Air Station out there. So they got garbage and they got dirt and they got a whole bunch of stuff, rock, right? And they filled the island of Alameda. They made it in the bay. You guys all know where Alameda is? Yeah, okay. So they made this island. Same thing with Treasure Island, right? As you go across the Bay Bridge, that little flat island down there, right? Same concept. They filled, okay? Because they put all this fill in, right, it's not the most dense, great soil to build on in the first place, okay? But it has a very high water table. If you've ever been out there, you know that the bay is, 4 or 5 feet below the top surface of those islands. Okay, so there's not a lot of distance. So the water table is only 4 or 5 feet down, right? Maybe 6 or 8 feet down on a good day from that top surface. And because that happens, if there was an earthquake, that particular island could turn to liquid temporarily during the earthquake, right? And then turn back into a solid. So if that were to happen, think about what would happen to a house or a building that was on that type of soil, right? It would want to sink, right? Or go through some major period of differential settlement, right? Depending on the type of foundation you have, could be big problems, okay? So this is something that does happen, right? That is a big problem, and that people are rarely aware of what it actually is, okay? But it's here, it's in the Bay Area. Just because Alameda is an area that was filled doesn't mean that this can't happen naturally somewhere else. Okay, so I use Alameda as an example because it's really easy to understand. Okay, but there are also areas with a very high water table where this same thing can happen just in the natural soil. Okay, so you just have to be aware of any place where the water is only 4 or 5 feet down. Okay, that means if you were to drill a well, you'd hit water. Does that make sense? Okay, so that's water table. We'll talk about water table a little bit more later on. Okay, so soils testing. You decide you want to build a building. You need to have some idea, right? We've now educated on the types of soils and how that might influence your foundation. So if you want to build a building, you have to somehow come up with an idea of what type of soil do you have. Therefore, how should you build your foundation in the first place? So before you even get to build your building, you're going to have to do some kind of a soils testing that's going to give you this information. Okay? How far down is the bedrock? What types of soils are there? So you can do a couple different methods of doing this. You can bring a backhoe out to the site and you can just dig a big hole. Okay? And in some circumstances that gives you enough information to know, okay, I'm in clay soil or I'm in, sand or whatever. You have a good understanding, you can proceed from there. Sometimes you need more information that's deeper and you don't want to dig that huge hole on your site. So you hire a drilling rig like this one to come out and they'll actually drill down into your soil and they'll pull up a core sample. Okay, that has a whole bunch of stria of the various types of soil. They'll send that core sample to a lab. The lab will analyze it and let you know how your soils is, that was totally bad grammar, how your soil will respond to various foundations, okay, the strengths of your soil. Okay, so we talked briefly about a water table, right, when I was doing my Alameda example. Okay, can anybody define a water table back to me? Anybody besides Evan? No guesses? Nothing? Yeah.
I would think that's where the water, after it rains and all the water collect, the level underneath the ground, where it's at.
Perfect. Perfect. Okay? So you nailed it. So a water table is just the level of the water. How is that? Okay, well, I guess I don't have the actual description. The water table is just the level of the water, right, down from the surface where water naturally seeks its own level. Okay, so the water table could be down 400 feet below the surface, if that's where water is, and it could be as high as 5 feet, right, 4 feet, 2 feet. below the surface of the water. So if you were to dig a hole, this is the easiest way to understand it. As you dig down, there will come a point, right, where you dig and you remove the dirt, and what's left of your hole will fill with water. Okay, that is what's called the water table. Okay, so if you have a really low water table, you can just keep digging and digging and digging and digging, right, and eventually you're 400 feet down and there's the water. Right? If you have this high water table that's right up at 4 or 5 feet, you don't have to dig very far, and lo and behold, there's the water. Okay? And this can vary due to how much rain you've had lately. It can vary a time of year, right? So the water table is going to change depending on the time of year, and it depends on your particular area and how much water is there in the first place. Okay? This is why deciding where to drill a well is a real art. Okay? Because you have to know this kind of information naturally. Okay, so let's talk a little bit about excavations. These type of excavations are always necessary to build your foundation. So you need to be able to dig out the existing material so you can put in your foundation. Okay, so as we're doing an excavation, there are several types of excavations that we can do. Okay, the first type is called a benched excavation. Okay, and recognize these types of excavation and what you can use vary greatly on the type of soil that's used. In this particular example, because these sides are relatively steep, right, it is a cohesive or cohesionless soil? Cohesive soil, okay? This photo, same thing. It's a cohesive soil, right? Anytime you see these straight benches, okay? The thing about a benched excavation is it requires a lot more space to do it, right? So you can't just dig, okay, I want my building to go here, I'm going to dig just the footprint of the building, okay? If you need to do a benched excavation, you need a whole bunch more site to dig so that you can eventually put your building in the middle of this. Okay, it should make some intuitive sense. Okay, so what's called the angle of repose, right, is the angle if you drew a line across each of these points as it goes down to the base. That's called the angle of repose, and that's going to respond to the type of soil you have. Right? If you have sand, cohesionless soil, that angle of repose is going to be much flatter. Does that make sense? Right? If you have clay, it can be much steeper. So that's going to vary. Okay? Generally, this type of excavation is a lot cheaper than the other types of excavation. So if you can get away with it, you're going to prefer to do something like this. Okay? The problem is that a lot of times we're building a building where we don't have a really big site. Okay? Sure, if you're building your house, right, or you're building some kind of a tilt-up construction somewhere, you have a lot of space around you. Not that big of a deal, right? You can do that kind of an excavation. But let's say you're digging somewhere in a city, right, in between two other buildings, right, and you kind of need to excavate straight down. If you want to do that, you don't have the space on the land to be able to do that benched excavation. So instead, you're going to be stuck with some kind of a braced excavation. Okay? And a braced excavation generally means that you're going to dig straight down, and somehow you're going to support this wall from caving in on your particular site. So you have to think about that positioning and how you're going to brace it and what kind of impact that has on the site when you do it. Okay? So here's an example here, right, where we're digging straight down. You can see there's a little tractor that's underneath. Right? So this is a ways under the surface. There's the surface here. I'd say this is maybe 15 feet of excavation, maybe 20, something like that. Okay? But they need these kinds of braces that are holding the walls of the excavation apart. Okay, so let's talk a little bit about these types of walls that we're going to build. Okay? Two types, soldier beams, sheet piling. These are called shoring in general. Okay? Shoring just refers to that wall. Okay? So let's talk about each of these. So a soldier beam, right, and you've probably seen this type of excavation before as you're driving around. Okay? It's fairly common. So what's going to happen is they're going to take a wide flange, an H-pile they call them, right? And they're going to drive it down, right, into the soil. Let's see if I have another example. Perfect. Right? So they're going to take this wide flange here. They're going to drive it down into the soil, like these have already been driven. Notice the size here, right? Here's the person. Right? So it gives you some context for size. Okay? They're going to get it positioned correctly. They're going to drive it down into the soil. Okay? After they've driven that down into the soil, I forget whether I have, yeah, you can see it a little bit better here. Okay? The soldier beam is all the way into the ground. Then they're going to, in between the two wide flanges, they're going to lay a series of boards, right, as they excavate. Okay, so as they excavate down, you've got those piles that run much deeper than the excavation itself, right? You lay those boards in place. These boards are going to retain the soil on one side. Okay, so depending on how deep you go, this can be enough, or you may have to add other bracing. Okay, so this is called a soldier beam. Okay, you can keep going and just keep adding more wood, which is the convenient part about it. Okay, so sheet piling, yeah.
Do it matter, like, when you have the beams going into the ground, does it matter much if it go on the inside or outside in your?
It generally is going to at least be, let me go back to the drawing of it. It's generally at least going to be on the inside of the innermost wide flange. So you see this section here. Can you guys see this okay? You want me to draw it bigger?
What do you call that wall? The next, the
This
description of the second,
hold on.
right hand side? Yeah, what's that?
Here. These are, it says wooden planks or lagging.
Are those wooden planks set below the grade of the foundation, like a footing?
These won't typically, and we'll get to this, these won't remain after the foundation is set. These are a temporary system that's going to shore up the wall that's going to be removed after you pour concrete as
So
your
theoretically,
foundation.
you don't need to put forms below where the finished grade is gonna be anyways, right?
Right. So all you need, this is just a temporary way of retaining all the earth that's on the other side of that.
Okay,
There are permanent ways that we'll talk about in a second.
okay.
Okay, so let me just draw this really fast so that it's a little bit easier to see. Okay, so we're looking down in plan view, right? We have our wide flange. Like that, okay? We have our second wide flange that's going to be over here. If I can draw it even. Okay, the most common place that lagging, right, those wood planks is going to go is on the inside. This is the hole. This is the existing soil, right, that you're trying to retain. The normal place that lagging or that plank is going to go is going to be right inside here. Okay, that's typically where they're going to put it. Sometimes they'll put it back here, but it has to go either on this to press up against this surface or on this surface. They prefer this surface because it's locked in between these two webs, right? So it can't slide. That make sense? Where up here it can slide off and then cave in. Make sense to everybody?
Those are the beams, right?
These are the beams. They're going into the
They'll
ground.
come
this way.
through the surface of the earth too.
Right, they're coming back up.
Yeah,
this
so
way.
you can brace your wall that you're showing right now to it.
Right. You can attach bracing to these. We'll get to it.
That's
Okay.
a cold joint in, you pour that first and come back later and pour that wall second. You could
Yeah,
do that
they're
at the same
gonna
time, right?
they're gonna ram the piles, and then they have to excavate before they can add that wood planking.
Okay, yeah.
Right, and as they excavate, if they need
Okay,
breaking,
gotcha.
then they'll put the bracing in. Okay. All right. So you can see it here, kind of in action. Right, this is already the hole that they've excavated. These piles are long enough; they go down further into the soil, such that the length of the pile still retains the overturning moment of the soil. So we don't have to have bracing here, which is nice. Okay, but it depends on the type of excavation and the type of soil and what kind of pressures are acting on it. Okay, so there it goes in. So there's an example here, right, where these are on the back side of those. So it can happen where it's on the back side. Just depends a little bit. How many people have seen this before somewhere? Okay, good. You're being observant. That's what I ask in this class, okay? The next type that we're going to talk about is called sheet piling, okay? This is also very common. They used to have a great example a couple years ago out in front of the Concord Home Depot. They were redoing a whole sewer system, and they had a whole bunch of this. Then there was an example last year on, I think it was last year, I don't know, maybe it was the year before, on 680 when they were constructing the new bridge, right, going over the Benicia Bridge, right, when they were filling in the part that used to have those dips, okay, there was a whole bunch of sheet piling, but I don't have any really current example for you to see, so I apologize. Okay, but sheet piling, right, can be made of timber, okay, much less common these days, okay. Most common, it's going to be some kind of a metal sheet piling, okay, and it can also be precast concrete pilings that go together, okay. This is the most common, these metal sheet pilings. So corrugation of the metal, which you can see here, you can use this, Okay, the corrugation, there's a little interlocking joint here and here, right? So we have this piece that has this little joint there. The same piece flipped around goes this way, okay? And you can see it here. We've got the in and the out, right, of each of these pieces. Those pieces slide together, right, and can be rammed in just like those piles, the big H, right, the wide flanges. You ram them in by tapping them on top, right? They form a corrugated wall that can then support the soil that you're excavating. Does that make sense? Okay, so it's a slightly different method, but this can be an efficient way of doing it because you're not dealing with the timber, right? You can just, you ram these sheet piles in, then you dig out the center, right? There's not much else required, which is nice, right? So it's easy. This is very common if they're working on a sewer system or something like that. Okay, so it can be made out of timber and it can be made out of concrete. Most common is going to be this kind of sheet piling here. Okay, so we already talked about this. They're tightly next to one another. It can, most often than not, it's going to be removed after the fact. Sometimes they leave it in place. Okay, it's not going to be a stable enough material to attach to your building, but sometimes it'll remain in place as a retaining wall of some sort. Okay, so here's the example, right? We've slid all these pieces into the earth before we started digging, right? Then we bring our tractor in and we start digging in the middle. Okay, now in this particular instance, this height, okay, so we see this is about 12 feet or so, right, is too tall to support itself, right? So they've added these braces, and they're digging out around the braces. So it's not as strong as those H piles. Make sense? The soldier beam. Okay, so the next type of a retaining wall, and this is far more common during a like a big building, like a skyscraper or something like that. Okay, so what's going to happen on a slurry wall is you want to build some kind of a waterproof wall, right, a foundation wall, and you want to be able to start building it from the surface. Okay, so you're going to use a clamshell bucket, and you're going to dig this really thin channel that's a wall. That's going to end up being your wall. Okay? Then after you're done here, there's the clamshell bucket going in and digging further. Okay, this is out of your book, so you can reference this later on. Right? Then you put your steel reinforcing in. Then you use this tool that's called a tremie, okay, which is like a giant funnel with a really long neck. Right? This sticks all the way down into the bottom of your foundation. I should say, as this happens, I should back up. This is what this little line is. The reason it's called a slurry wall is when you dig down, this would collapse on itself unless you filled it with some kind of a slurry material, okay, which they manufacture on the site. It's kind of like really thick mud. Okay, so you fill it to hold the wall apart. You insert your steel cage. You use your tremie. You start with concrete at the bottom, pull up. At the same time, all that slurry material comes out. Right, so you have to deal with that, and then you end up with your concrete wall, which you're then going to apply with tiebacks. So we'll talk about it in more depth, but that's the image that goes with this description. Was there a question? No?
I'm sorry.
Okay. Okay, so you're going to start with this clamshell bucket, right? Sometimes it's between two beams that you've cast on the ground in concrete just to keep it straight. You can imagine working with a clamshell bucket would be difficult to keep it straight if you didn't have some guide to work with. Okay? Then you're going to add this bentonite clay slurry, okay, which, like I said, is just like a really thick mud kind of thing, okay, but it's slurry enough so that you can dig through it and pull up your earth. Does that make sense to everybody? Okay, I'll show you some pictures in a second. Okay, once the trench is dug to the desired depth, you're going to keep adding this slurry, right, to make sure that it doesn't collapse on itself. You're going to put the cage, the steel cage in. Okay, can be rebar, can be a welded wire mesh. For reinforcement. Then the trench is concreted from the bottom up with what I call the tremie, which is that funnel, right? A funnel and a long hose. The reason you're doing that is you want the concrete to start at the bottom and then to be able to basically push the slurry out as you fill it with concrete. Okay, that's when it's going to give you a nice solid piece. If you put the concrete in from the top, there would be no place for the slurry to go out. That's the problem. Or the concrete would separate as it went through the slurry as it sunk to the bottom. Okay, the reinforced wall is tied back as the excavation continues. Okay, we'll talk about that in just a second. Okay, so why or why not use a slurry wall? We'll get to that in just a second. Well, I guess we'll do it now. Okay, so slurry wall, okay, it's very, very expensive to make it, but one, it's waterproof, and two, it's something that can long-term be part of your building's foundation. So it's designed to be part of the foundation rather than something that's removed, right? So you go through this extra effort and cost, you can eventually use it as part of your building, okay, which is the big advantage. Okay, this is an example of a slurry wall excavation here, right, where we've got outside grade parking lot, right? This is the slurry wall as they excavate down. It looks like a concrete wall, concrete retaining wall. Okay, so let's talk about how you're doing it. Okay, this is mixing up the slurry before they're even going to dig, right? So that it's not the cleanest process. Okay, here's the clamshell bucket. Okay, so you can see the two little poured concrete beams that are helping to guide this big bucket straight down. Okay, you can see where if you didn't have those, it would want to twist to one side or the other, and you wouldn't get a straight wall. Okay, so you have those two pieces. It comes down, hydraulically scoops, pulls up, dumps out the remaining material that you just dug. Okay, as you go down, right, you fill with that slurry. Okay, here's an example of a finished slurry wall. Okay, I believe this is in Las Vegas, some part of a casino, right? You can tell. Let's see if we can find any little people. There's a little person, right? Really, really tiny. Okay, you can tell the cranes and that sort of thing, right? This is one of the really big excavators. Tiny. Okay, so this is a pretty tall slurry wall. It's retaining a lot of soil, and that's the advantage of it.
So that was under the earth at one time?
This whole
That whole thing was under
piece was all under the earth, and so they got rid of that. Yeah.
The slurry walls don't necessarily have to go underneath the excavation because they're tied back, correct?
Correct. Right. So they tend to go a little bit further than where your excavation would be, so that you don't get any undermining, right, of the soil. So they're always going to go a little bit further, but the tiebacks are going to keep it in place, right? So it's not going to either overturn or undermine. That's the concept of it. So they don't have to go too much deeper than your excavation
Those are
would be.
pretty strong walls there.
They're very strong walls. They're very strong, which is why you could eventually build your building on top of those walls. It's basically a concrete retaining wall. You're just constructing it from the surface rather than digging and then forming and then pouring the concrete, which we'll get to later on. Yeah.
What keeps the wall, the finished wall smooth?
It's not a finished quality wall. Okay, so when we think of, like, the concrete that we see, right, it's been cast against some kind of formwork that's going to have some kind of a texture on it. Generally, it's really nice to look at. Okay, something like this is going to take on the texture of whatever the dirt that you excavated. Okay, so in some cases it may be fairly smooth, in other cases it may not be. Okay, so it's not really that pretty of a wall. If it ends up being a finished wall, they will put some kind of a fake wall in front of it that will give it its finish, or they will grout it or stucco it or something like that, right, and cover it up. The other problem is we've got these tiebacks, which we're going to talk about in a second, which stick out from the wall, which would be another reason that they put something in front of it to cover it up. So it's not really a finished quality wall, but it's finished structurally. Okay? So we're going to take a break from that for just a second. We'll come back to it. And let's talk a little bit about bracing. Okay? So if you don't have the slurry wall, right, or even if you have the slurry wall and don't want to go to the expense of using tiebacks, you can use a variety of types of bracing. Okay? And this is more common in older excavations, right, because we have better technology to do the slurry walls today than we used to. Okay? So there are three types. We've got cross-lock bracing, we've got rakers, and we've got tiebacks. Okay, and we'll talk about each of them in depth. So cross-lock bracing are just temporary wide flange, or I-beam, so to speak. I-beams have been replaced by wide flanges. We'll get to that when we get to the steel section, right? That are laid across, right, and then support to the other side. Okay, so we have them running lengthwise, and we have something in between, right, supporting walls on either side. Okay? The problem with this is you have all these braces, and somehow when you go to dig, you have to dig around all the braces. Okay, so it's cumbersome to work there. So generally it's inexpensive. Okay, so here we are, right, in the cross-lock bracing scenario, right? We're using that clamshell bucket here just to dig out the foundation because we can't drive a tractor in there, right? Because we've got all of these bracing happening. Okay, so that's the disadvantage, but it tends to be cheaper to do it that way. Okay, so here's an example of cross-lock bracing. This is a little bit of a cheater example because it's just in the corner, right? But here we go. These are steel, hollow section steel instead of wide flanges. Doesn't really matter, right? Basically steel tubes in translation. We've got our wide flanges here, and these steel tubes are protecting the corner. But this gives you, again, some idea of the size of these excavations, right? We have the little person here, and you see how deep this excavation is. Okay, so the next type of brace is what's called a raker, right? And a raker is if you have an excavation that's too big to be able to do a cross-slot bracing, right? You have to have really long pieces of steel. You're going to do what's called a raker. And a raker is just a diagonal piece that braces from the wall down to the earth against some kind of a temporary block or footing, right? So if we jump back a couple slides, here you can see rakers in action, right? So we've got this temporary piece that comes down to a block, right? And all the weight is pushing from the soil here, goes down this to that block, and the wall doesn't collapse. Okay? But this is too wide to be able to run a beam all the way across. That's why you'd use this. Okay? So sometimes on a site like this, you'll see cross-slot bracing in the corners, but once we get out here, right, we'll use the rakers instead. Okay? So there's always going to be a little bit of a mix, and that's okay. Okay? Just like with the cross-slot bracing, if you have all these members coming down into the middle of your site where you're doing your excavation, they're going to be a big hassle. Right? Furthermore, the more earth you dig out, the more you're going to have to change where these braces go in the first place. Right? Because they're resting on something. So it's kind of problematic. Okay, so here's an example here. Right? We talked about cross-slot bracing occurring in the corners, and here are our rakers coming down, right, and supporting this particular stretch of wall. Okay? Okay, so tiebacks, which you heard me talk about a lot with the slurry walls, right, are the most expensive to do, but they take up no space in the site itself, which is the big advantage of it. And often they're used with slurry walls because they're not temporary bracing, they're permanent bracing for the slurry wall. That make sense? Okay, so what happens is that you're going to drill a hole, right, at a specified interval, right, through the slurry wall, right, this hole comes down, very deep, okay, there's a little break line here, right, very deep back into the soil, okay. After you've drilled that hole, right, you're going to insert some steel cables, tendons, right, into that hole, right. Then at the very end, you're going to inject some grout, which is basically like concrete, right, which is going to bond to the steel, right. Theoretically, you could fill up this whole piece as well, okay. It's going to bond to the steel, bond to the earth, give you some friction to pull against, right? And then you're going to use a specialized hydraulic jack, right, that's going to put those cables into severe tension, right? And then you're going to insert this little block, right, on the wall that holds that tension, right, when you release the cables. Okay, and it's going to press that wall in. Does that make sense? Okay, so you've got this really taut tension cable with the grout at the end. There's your little piece. So this is all that's protruding out into the excavation of the site. There's no braces, there's nothing else. So this is the excavation area here. Yeah.
In the book, it talks about how your footing isn't allowed to cross your lot line because legal issues like that. How do, in really urban conditions, how do they get away with doing this? Because obviously...
My guess is this is an exception. Okay? Yeah, because theoretically this is going way over into the other person's lot line.
Yeah.
Because it's not surface level, you know, it's subterranean. You know, I don't know. I'm not a you know, construction lawyer in terms of this kind of land use, but my guess is that this is something that's permitted. Certainly, if your neighbor has this, right, and you, right, this goes into your lot,
Yeah.
right, and then you decide you want to dig down, right, and want to put it into their lot, which is already an excavation, that's a big problem, right? So at that stage of the game, you'd have to reconsider how this building is going to work in the first place, because those tiebacks are no longer going to work. This middle wall between your two buildings would become a joint wall, or you'd have to build two separate walls or something. Okay, so there are tricks to it. Yeah.
There's a plate that the cable's going through that against the earth, right? Like a large plate, like.
Yeah, it can be. Usually, it's a smaller steel plate that's against the slurry wall.
Right.
Okay, so recognize that the slurry wall should be here, which is really funny because on this drawing they don't show the slurry wall that it goes through. Okay, but that plate should rest against the slurry wall, which is then spreading the weight of that tension out.
And then there's structurally another cable.
Right, so I'll show you an example here in just a second. Okay, so here we are here. This is not, right, in a slurry wall, right? This is in those soldier beams that we talked about with the H-piles. This is right on one of those wide flanges, right? And that tieback is going back into the hillside from here. Okay, so it's not always a slurry wall, it's more commonly a slurry wall. So here's that giant excavation that I showed you several slides back. Okay, these are all those little tiebacks. Okay, so they're going to vary at intervals. Notice they're a lot closer together at the bottom, right? A lot further apart at the top. The engineer specifies the placement of these, right? So you're going to engineer this foundation and this slurry wall. It's not just something that the contractor decides, oh, I'm going to put another one here, right? It's very specific about where those tiebacks go. Yeah.
How far in tiebacks go on something big like that?
How far do they go back?
Yeah.
Could be 50 to 100 feet, right? Could be less. Depends on the type of soil. That's always the big concern. Okay. If they go far enough back so that the friction along the length of that grouting will hold, right? And that depends on the type of soil that you're using. Yeah.
You could put those drill those cable denials all out, you have removed the earth away and expose.
Right, you don't put these, so the slurry wall, okay, so let's say we start and recognize this is a gigantic excavation, okay? So we put our slurry wall down, we dig this whole thing and we put our slurry wall in, okay? After that slurry wall is there, we start excavating from the top. And as we excavate, when we get to about here, we go ahead and put this row of tiebacks in. Okay, then we keep excavating and we get to about here, then we put the next row of tiebacks in. Okay, then we excavate more, we put the next row in. So it works its way down, so you're always adding that reinforcing as you go down. Yeah.
So the tiebacks are like pretty much permanent, right?
Tiebacks are definitely permanent.
For the crossfire racing and the rackers, or you take those out later on? Right?
You take those out. So what happens is when you dig a hole, right, for this excavation, you're anticipating building some kind of a foundation in the hole. That's the idea. Okay? So if you're using cross-lot bracing or you're using the rakers, that bracing is temporary until you build whatever foundation walls you have. And then once you've built your foundation walls, then they're going to retain the earth and support your building. Okay? In something like this, because the slurry wall is its own structural piece, right, you can build your building on top of it. This is the foundation wall. Therefore, these tiebacks become permanent. You're never going to take them down because that's what holds your building up in the first place. Yeah.
Will you use any of the temporary bracing with the slurry wall?
You can, and you may do it sometimes as you're digging if you need that temporary bracing. It's designed so that theoretically, if you dig only this much, right, then you put the row of tiebacks in, you shouldn't need it, which is a big advantage when you're working on the site because there's nothing hindering your excavation of the site. Right, it's easy to work in that site itself, which is the big advantage. Yeah.
Generally, to get the tiebacks into the ground, how many would you use?
It'll be a long drill like that. You saw the core drill, right? That a few slides back about taking out that core sample. Same concept. It's going to be a really long drill that's on an angle, right? That drills through that slurry wall and all the way into the earth. Then you insert your cables and you inject your grout. Okay. Then there is a special machine that comes and tensions the cables and slides the
You
plate
say
on.
you inject the grout
After you've drilled it.
oh,
Okay, because what happens is you've got to drill the hole, you've got to then get the cables all the way to the bottom of the hole, and then you need the concrete to go around the cables. Right? So I've never done this personally, so I don't have any first-hand knowledge of the exact mechanics required to do it, but the order is that.
I didn't know if it was grout or cement.
It's called grout, and grout, when we get to the concrete section, we'll talk more about the difference between, quote, grout in this context and concrete, okay? But grout is usually just a no-slump, high-strength concrete, okay? And we'll talk about that when we get to concrete, so you don't have to remember that just yet. Okay, so the thing about excavating, right, we already talked about that pesky thing called a water table, right? You did a great job defining it. Okay? If you're going to excavate this giant hole and there's a really high water table, you kind of have a problem, right? So, for example, let's say you're building the new towers where the World Trade Center was in New York, right? There's a really high water table there. So somehow, as you're working, you're going to have to get rid of that water from your site so you can actually work, okay? So, I kind of emphasized, but why would you need no water in your site?
For your foundation of it.
Right. So you can actually work in the site, you can build your foundation, that sort of thing, right? So we need to get that water out. Okay. So how would you get rid of that water? Okay, we've got pumps. Any other ideas? I can't hear you. You just have to speak up. Come on.
Wells, no different type.
Okay. You're on the right track. Wells are good. I'll take wells. That works for me right now. Yeah.
I would guess just like pumping it out.
Yeah. Pump pumps, wells, that sort of thing. Also, if you build a slurry wall, that becomes a waterproof barrier, which is helpful. Okay, so we'll talk about that. Okay, so excavations need to be kept dry so you can actually work, which should be relatively obvious to you. Okay, so dewatering often occurs using pumps and what are called sump pits. Okay, so the problem with pumps, does anybody have a sump pit at their house? Okay, I do, right? It sometimes happens, it depends on how much water is around your house. Okay, what happens is you need a place to put the pump. If you're going to put a pump, right, you need a place where the water is going to collect, which you can put your pump in and then pump the water out. So they dig what's called a sump pit, right, which is just a simple hole in the ground that's lower than everything else, so water flows into that hole. You put your pump in that hole, and you pump the water out of that hole. Make sense? Okay? So, so what happens with this collection hole, this pit, okay, is you're going to wait for the water to accumulate enough, and then you're going to pump it out. Okay? If the water's coming in fast enough, your pump can run all the time. Okay? If it's not, you need some kind of a switch that activates the pump when there's water, pumps the water out, and then shuts it off when there's no water. Okay? The other thing is you can drill what are called well points, right, which will depress the water table. And I'll show you a pictorial example. So Alexis, this is what you were talking about. Okay? And the other thing is you can use a watertight barrier to help prevent water from coming into the site in the first place. Okay? Which is another good way of at least giving you something. Now recognize if you're excavating the bottom of the site and there's a high water table, the water is going to come up from the bottom. So this isn't going to solve the issue, but it gets you somewhere. Okay, so here's our sump pit, right, to collect and move water from the excavation. Here's our little pit. There's a pump in here that's going to pump the water out. The problem with this is that your pump can fail, right? The electricity can go out. You can run out of gas if it's a gas pump. Your generator can fail, right? There's lots of problems, and if that happens, you have water on your site, you can't do work. It's a problem, okay? They're also, okay, you're pumping all this water out, you have to get rid of the water somewhere. So depending on where you're working, you can't just like open the sewer and pump the water into the sewer, right? You have to figure out how you're going to get rid of that water. Sometimes there's toxins, okay? Say you were doing this in Alameda, right, on the Naval Air Station. That whole land you're not even allowed to dig on because it's so full of toxins, okay? So that's a big problem. If you suck the water out, you've got all this toxic water. What are you going to do with it, right? So that can be a problem, okay? The other thing is there's always going to be water in those pits. So you're always going to have some water on the excavation site. So what happens if you need to work where the sump pit is? Okay, that can be problematic. Okay, so well points are a good solution that's not quite a sump pit, but does virtually the same thing. Okay, so we have our excavation, and what happens is we're going to drill a ring of wells, right, around the site, and they're going to be below where the water table is. There's the original water table. Okay, and we're going to start sucking out of each of those wells. And as we suck out of each of those wells, right, the water table is going to dip, right? It goes back up in the middle, right, and then dips here, so that the water table goes down because you're pumping all the water out. Okay, so you're drying out the site without having to have a sump pit in the middle of the site pumping the water out. Okay, sometimes if this isn't enough, you'll need several rings of these pumps as they go further and further out from the site to be able to, and deeper, right, to be able to pump all that water out and keep your site dry. Does that make sense? So they can be concentric rings. Yeah.
When would the pumping actually be occurring? I mean, you wouldn't leave it running throughout the whole, excavation period.
You would leave it running during the whole excavation period until you poured your foundation with some kind of a waterproof barrier, right? That keeps the water out of whatever that is. Now, these types of excavations, we're talking large-scale buildings, so it's going to be parking garages and building utilities and that sort of thing, the things that occur underground. Okay, so that's the scale. So this is not something that you're going to be doing much of if you're building a house or something like that. Okay, this is a bigger scale than that. Okay, so just recognize that you can have these, but the same problems still exist with these well pumps. You still have that water. You still have to be able to get rid of it if it's toxic. If it's coming from a well like this, it's more likely to be less toxic than if you're pumping it out of a sump pump because you've got construction debris and mud falling into the sump pump, as opposed to this is theoretically a relatively clean water source. Okay, but again, it depends on where the building is. So we already talked about there can be several rings of these pumps. Okay, now recognize if you have a very small site, right, and you're trying to do this excavation, and you need to drill these well pumps, and you don't own any of the property around it, it's kind of challenging to drill all the wells that you need, right? So there are challenges. You need to have enough space to do this method in the first place. Okay, so the last example, right, is to use slurry walls, right, to form a waterproof barrier, right? And what you're going to do here is you're going to dig the slurry wall all the way down to where it gets to an impermeable. Can't talk anymore. An impermeable layer. So think bedrock, right? So you dig a really deep slurry wall, right, all the way down to where it hits the bedrock, where the water can't seep around it, right? Water stays on either side. It's a waterproof barrier. You can excavate to your heart's content in the middle. Okay. Note that this would obviously be a really expensive thing to do because the slurry wall is much bigger than it has to be. Okay, which you can see from here. It's almost twice what it needs to be. Does that make sense? Okay, but it does work if you don't have any other option. Okay? Okay, so here's a watertight barrier with a slurry wall. Okay, and we've got, this is in Dubai, as an example, okay, which has a high water table, correct? Okay, you guys are somewhat familiar with Dubai. Right, we've got the tiebacks working, right? Notice there's a little leak here. Right, so we've got some water flowing in. So there's going to be a sump pit. I'm going to zoom in there. We've got these hoses that run up over to pump the water out. So we're doing well. Okay, there it is with our little close-up here. So we're getting some leakage. Right, and this is a little more than a little leakage. It's kind of challenging, right? So this pump is here. Right, here's our tubes going to other pumps running up, and we're trying to suck out. There's a sump pit right here. We're trying to suck out all this water, right, and get rid of it. Okay. So again, slurry wall. If I were building this and there were these stains coming down, I'd start to get a little nervous. I don't know about you, but I'd be a little nervous, right? So maybe you didn't do a good job dewatering and something like this might happen. Right? So this is that same slurry wall. This wasn't a strong enough wall. It didn't have proper tiebacks. Recognize the tiebacks wouldn't really work over here because you're going into water instead of earth. Right? So this is problematic. Right, something like this can happen. So this is the canal on the other side of this excavation. Right, you can still see all of the cranes and that kind of stuff, and so you end up with this. So this is a little problematic because you're set back a couple years probably in your construction process, right? So you don't want this to happen. So the point of these kinds of images is just that dewatering is really, really important, right? Because obviously you can't do any work in this kind of a scenario. Okay. So that's it for the first section of the class. Do you have a question?
You never mentioned where when they hit the water, what do they do with the water?
They have to find a way to dispose of it.
Where
And that's dependent on the site. So sometimes it goes into trucks and they truck it away to somewhere where they can, dump it. Sometimes they can, dump it into the groundwater system. Sometimes they can take the water that's pumped here, pump it out into another body of water. It depends on how toxic that water is as to what they're going to have to do with it. Certainly if it's really toxic, they're going to have to figure out a way to, filter it or dispose of it in a good, clean manner. Recognize that this water often can be muddy and icky, and that's a problem too. Okay, so I believe, that's it for the first section. So we're going to take a 15-minute break. I don't even know what time it is. It's 10 minutes to 8, so 8:05, come back, grab yourself some coffee, get a stretch, all that kind of thing. All right?